It's a pleasure to have Pedram giving us the first colloquium of the new year. So Pedram got his PhD at Princeton in 2011, working with Ali Yazdani, applying SDM to topological insulators. Then he joined Martinez's group at UC Santa Barbara and switched to working with superconducting qubits. Then in 2014, he joined with the rest of the Martinez lab. He moved to Google. Basically was part of the founding, researchers of the Google hardware lab, quantum hardware lab, and has been there ever since. I've been basically a major contributor to many of the most important quantum simulation projects at Google since then, and his main interests these days are basically simulation of exotic condensed matter systems and non-equilibrium phenomena. So with that, Pedram, please take over.
Thank you. Thanks for the invitation and thanks for the introduction. I'm very happy to talk about some of our latest works. I think the last time I talked at Brookhaven was about the beyond classical work, so I want to pick it up from there. That was maybe a few years ago. In 2019, our team, which you can see a picture of them right before COVID time, performed this beyond classical experiment, and it's become, to some extent, a very turning point for us to think that quantum processors have this capability to do beyond classical experiments. So what else can be done? And as we are celebrating, also we are kind of looking into future of what are the other possibilities and whatnot. And this talk would be a bit focusing on those concepts and works that we have done ever since. And feel free to ask questions anytime you like and stop me. I don't see people's faces or chat box, but I'm happy to answer all questions you have anytime. But I managed to, let me make a disclaimer before moving forward, that I'm deviating from the original abstract that I sent around. And I'm going to split this time between a little bit between how NISQ discovery looks like and how what's the relevance to error correction and how we have made some of our recent progress in terms of the error correction works. But since I managed to confuse people sufficiently enough, I want to emphasize that I think except one slide, which we may not even get to, everything I'm showing are mainly experimental results, and there's no, this is not a numerical simulation talk or anything. It's all started from making Josephson junctions decades ago, and what we do in the lab is essentially exploiting this physics of Josephson junctions to do many-body physics. We don't need to go through the detail of how these nonlinear resonators are important component of the work, but the fact that I'm showing you a couple of pictures is to give you the sense that the fact that we can control them, which is the essence of quantum is because these are macroscopic objects. So you can really bring wires to them, and you can essentially send microwave pulses to these wires. And by sending microwave pulses to these wires, essentially you would be controlling the Bose-Hubbard Hamiltonian. And that's the physics we do. We do have some work, particularly just working with microwave photons under Bose-Hubbard Hamiltonian. But majority of this talk is about pulsing these couplers and individual qubits to make individual single qubit or 2-qubit gates. And here are the couple of examples of the devices that we used to make. This is the extent you can go with one-dimensional objects. And nowadays, we are working on 2D geometries. And 2D geometry means that you can you have to put two chips on top of each other, one for wiring, one for one for the qubits and resonators, readout resonators, and then you would not be able to see how things are laid out, and I don't want to show that anyways. But when you're confined to 1D, you can see the structure very clearly in front of your eyes. And here, for instance, you can see a picture of a 9-qubit chip and the readout resonators on top of them, and the coupling. The same picture I'm showing twice. One is a little zoom in, and you can see that there are wires coming from below, and we can tune every terms of. We can look at them.
If I may interject, everyone, please mute your microphones, please. Please continue, Pedro.
Thank you. So this chip is I don't know, more than 5-6 years old, but the essence of the physics is the same. And the story you're about to hear is a story of interacting microwave photons in these platforms. Some people like to refer to it as cavity. I don't know where the cavity is anymore. Again, the starting point is this beyond classical or supremacy work in 2019. And you get about 53 qubits, and the error rate is about 1%. And you can define a contrived problem. You can contrive a well-posed question, in fact, and you can solve it on a quantum processor and show you can solve it faster. That's the story of that article. But the question is, what can you do? So going around and asking questions, we came up with these couple of categories of physics or chemistry problems that we can address. One category would be to not make many more qubits. Look at the horizontal axis is linear. You just make twice more qubits or so. And then, but you have to make exponentially better qubits, order of magnitude better qubits. And then you will be able to solve some problem related to interacting electrons or generally ground state of big chemical molecules and whatnot. But the non-equilibrium dynamics, interesting problem in magnetism and Floquet dynamics could be something more closer to what we could do. And that would be, in fact, constitute the first example I would go over. Another approach, which I would touch not much on it, is that you don't make qubits much better, you make many of them. And then these would constitute a logical qubit of 10,000s of qubits would be 1 qubit, and you use some error correction scheme. And that would be a subject for a different talk, and that's not the focus of current talk. So since I made this plot 3 years ago, we made several articles, we finished several projects in exploring in our way through this landscape. And here I'm talking about one of them. And if NISQ processor, this noisy intermediate scale quantum processors are meant to give any result or give any hints of any discovery, we should see it by now, right? The term NISQ was coined, I don't know, more than 5-6 years ago, maybe in 2016, if I'm not 2012, I forgot, by John Prescale. And it's really the time to see what really can be done, and if there is any fruit in this, that we can pick up in this landscape. Although I have to admit that people disagree on what definition of NISQ is and whatnot. The first work that I'm about to describe to you was published in last year, and you can see it's mainly done by everybody at Google. This is the sign to represent 100 some number of authors, 160 number of people or so. But then some of my colleagues took a more active role and dedicated much more time to this project. And this is the fruit of this collaboration. So when we look at this landscape I'm showing you, we are looking for hard problems to solve. And the first hard problem that we solved, as I mentioned, was highly a contrived problem that we knew what's going to be hard on a classical computer and easy for quantum. So we just defined it as a problem and we solved that. But now it kind of begs us to go back and think, what is the origin of hard problems. In fact, the origin of the hard problems is the number of particles that are interacting with each other. So it's very obvious that we have to go and jump into the interacting systems of particles. And in the classical physics, even, we are very familiar with the concept, with the Poincare-Bendixson theorem that tells you that unless you have 3 particles at least, there is no hope of even chaos or anything. It's just 2 particles is rather solved. That's by Newton. And then 400 years later, we still not only we didn't solve three particle physics, but we only prove that we can solve it statistically in certain limits, and we cannot solve it. So when you come to quantum systems, the same underlying principle applies in here. When you look at the ocean of interacting systems, most of them are really non-integrable. And then they have tiny solvable problems, which we call them integrable. And that's exactly when you have a scatterings. All the scatterings can be factored into 2 by 2, 2 in, 2 out scattering. So it goes back to 2-body problem. So that's, well, intuitively or very hand-wavily, the sets of problems we can solve in the quantum problem is very similar to the only solved problem in the classical mechanics. So that would be our starting point. We're not just going to jump into an ocean of interacting problems which are not integrable and not to know what to do. We are going to rest our intuition based on integrable systems, which are essentially a set of measures 0 in the ocean of interacting quantum systems. But there's also an interesting problem as an experimentalist. When you look at these tiny islands of sets of measure 0, which you realize that theorists cannot get away from those islands easily. Of course, for as an experimentalist, you can change parameters rather easily and tell you what happens. And that's what we would do toward the end of this part of the presentation. So in a sense, there is an Achilles heel, which is integrability breaking for theorists, but the ratio of the surface area of the air that there are vulnerable to arrows is very different. You have tiny islands of integrability, or rather sets of measure 0, and then most of the places are just non-integrable. And think of Achilles, that every part of its body was actually would be susceptible to an arrow. It's exactly the other way around. So the problem we chose is this a formation of bound state in Heisenberg Hamiltonian. So Heisenberg Hamiltonian is a century old or more. Analytics written by Beta Ansatz. It dates about a century ago. But then you can assume when there is a bound state, when some system is integrable, you can assume the bound state exists in most of the cases, I guess. I don't know how accurate I can be with this argument. But observation of the bound states had to wait for about, or showing that where they exist and where to look for them. An observation of them had to wait for about a century later, and happened in the lab of Emanuel Bloch. Now, so XYZ Hamiltonian supports bound states and has been observed. What about the Floquet version? If the Floquet version of the XXZ model is that integrable, and that question was answered by a team led by Tomasz Prosen. And essentially what I'm talking is that you apply the XXYY term of the Hamiltonian, and then you apply the Z term of the Hamiltonian. So I'm having it in here on the right side, that you can see we are doing the kinetic term first and then the hopping term next. And in the limit of theta and phi being small, this is the Trotter's expansion of the Hamiltonian, but we are not going to stay for these small theta and phi. We're going to make them as big as we want. So it was shown as integrable in 2019, and then Igor Aliner from our team showed that there eventually he wrote the analytical form solutions for the bound state for this case too. So with the analytical solution in hand, we went to the lab and tried to implement this Floquet version of the XXZ Hamiltonian and see if we can find the bound state. What is the significance of the bound state, why they're interesting, is that usually when you're thinking about an electron hole or some other excitons bound states, the stability of them usually coming from them being located in a gap, energy gap, meaning there is no energy nearby for them to decay to. And Fermi golden rule tell you that since there is no energy overlap, there should not be any decay. But imagine you have bound states in the presence of the continuum, and that is protected essentially by the symmetries of the problem. And that is really something novel and something interesting. And again, the work of Emmanuel Bloch is a manifestation of that case. And I'm going to extend this to Floquet dynamics, where instead of energy on the vertical axis, now I have quasi-energies on as complex angles on a circle. And I'm telling you that where the band, there's a continuous energy, are we going to see stable bound states? And this coexistence and being stable is really the theoretical beauty of this physics that we are about to explore. If I have a chain of qubits, and I excite couple of qubits, meaning by putting microwave photon on them, are they going to stay together or not? Are they going to be bounded or not? They are going to hop together, and then the later state of the system would be the superposition of many of them. So every time I do a measurement, I take a snapshot of this large superposition. And the question is, are the bit strings I'm going to find would be of this kind I'm showing in here, meaning that the excitations are indeed next to each other. So that is my experimental definition of what I mean by the bound state, or how I'm going to hunt for it, at least initially, and then I'm going to go deeper into the momentum space picture too. So that's the setting of the problem. Before going and attacking the problem, I want to give you an intuitive reason why the presence of this interaction term circled in or highlighted in red square is important for formation of the bound states. So that's the physics we are going to do. For the photons not ending up together, let's say you have two photons starting together and they end up not together at some later instance of time. I'm using some hand-wavy argument based on Feynman path integration, which says that if you start with this configuration, they are together, and then later configuration that they are not together, then you have to consider all possible paths that connects these two configurations. Which means the two photons stay together for a while and they separated. And the point of separation could be of any of these steps they took. So here we are talking about a chain at different instance of time. The vertical axis is chain in different configurations, and the horizontal axis is the chain repeated in time. Okay, and you see when they are together, they are accumulator phase. And when they stop being together, this phase accumulation down to this last term goes away. So eventually, for this configuration, the probability of this configuration is summation of all these paths, which are add up with these different phase factors. And since these phases are random numbers, you would see a destructive interference. So mean that starting from this configuration and breaking apart is suppressed. So this is a hand-wavy argument that works sometimes and doesn't some, but at least tells you that how the presence of interaction could lead to formation of bound state by suppressing these kind of scenarios. So what we are going to do, we are going to take 24 qubits and carve out of our 2D grid of qubits. We can turn off certain qubits and take them out of the grid, and we can form a ring of qubits, which qubit 24 is connected to 21. It's not a difficult job to do without needing to fabricate anything. And we are going to excite qubit 1, qubit middle, qubit 12. And we are going to say, where is my photon? Where is my microwave photon? And here we excited one qubit, or we put one microwave photon, and there is nothing for it to bound to. So it would perform a very happy quantum random walk as a function of depth. And there is this is non-interacting, nothing to interact with, and you can very simple interference pattern that you can enjoy. When qubit 24 hits qubit 21, when it propagates all the way through the chain, it bounces off each of this wave function. Not the wall, but you know what I mean. It just continues its path essentially, and appears from the other side. Now we put two of them together, and then there is a chance for them to form a bond. And you can see indeed the concentration of the color, which is where I found the photons, is indicative of the fact that they are staying together and they are propagating slower. And I put 3 and 4 and 5. By the time we put 5 excitation together, you can see that essentially these seams are together and they're not moving anywhere. So let me analyze this further. This is not the strongest evidence for forming a bound state, but let me tell you what we can do further analysis. The bit strings I get in every case has NPH photon in it, and I can sort my bit strings into two buckets. One is the bucket that the photons are together. Another is the bucket that they are not together. So they're separated or they are together. If I just focus on the bit strings that they are together, forget about the others, put them in the trash can, you can see for the case of 2 and 3 and 4 and 5, I repeat the same non-interacting case very clearly, indicative of the fact that they are staying together and they are jumping together happily. They are jumping on this lattice from time to time, and they're leading to this interference pattern that we are seeing in here. But notice every measurement repeats a bit string, and then you can just add up the numbers you got. So every T bit strings look like this one, and S bit strings look like the ones that still have the 4 photons, but the photons are not necessarily in adjacent sites. And well, we can further analyze this and extract these slopes, and it's consistent with the theoretical predictions of coming from the paper from Igor, and this is really consistent with them being together in the real space. But some of you being condensed matter physicists, I want to say how much we can go and talk about band structure formation in these systems, and what can we say about effective mass and these parameters that you are probably more familiar from your neutron scattering or ARPES or quantities that are dear to the heart of condensed matter people. Well, but I need to tell you a little bit of elementary quantum mechanics. I just tell you about two very specific examples, and I leave you to generalize it, and you can see by that you can see the limitation of the method too. Let's say you have a Hamiltonian and it's have eigenstates and eigenenergies. So for now, let's just focus on Hamiltonian. And if you have initial states which evolved under this Hamiltonian, there's nothing fancy, it's written in here. If somewhat we could get the overlap, is a complex number, overlap of the initial state with a wave function evolving, you would see exactly what you like to see, meaning that you would see the eigenenergies of the problem. And some prefactor, which is set by your initial state, and then a bunch of exponents that are adding up. And you can see the Fourier transform of this would give you exactly the eigenenergies of the system. So this complex number have different frequencies to it, which hopefully you can extract that, and you can see the component of the Hamiltonian. So let me tell you what it means in the lab, meaning that you put one qubit on the equator. That's a non-interacting limit I'm describing now. So you create this superposition, and at the end of the day, yes. And at the end of the day, you measure some non-Hermitian operator. Okay, it's not intuitive. You measure two distinct measurements. It's like constructing the green function response of the system. And if you measure expectation value of this operator for this initial state, you would get exactly this complex number that I'm showing you here. And you can go a little further. You can do for 2 photon case. You put 2 photons on the equator, and the observable to measure, it's 4 distinct Pauli operator things that you have to measure. And again, the Fourier transform of that observable would give you exactly what you want. So you can go up to a few photon in here, and you can see the expression for it getting more and more complicated. And that's how far we can go with this idea. You can, and we show you we have gone up to 5 photons in here, which means you have to measure 32 Pauli operators in here, and construct this observable by, well, sorry, this operator, which is not observable, by adding them up with proper plus and minus I factors, and move forward. So let me show you how it works in the lab. This observable that I'm mentioning in here, let's say sigma 3 minus sigma 4 minus, can be measured and as a function of sight, as a function of time, and it looks like nothing. However, when you add them up with the proper prefactor I mentioned in terms of I and minus I and 4 of them, and you Fourier transform them, the 2D Fourier transform, you see a very clear band structure. So this is just a Fourier transform of this signal, which looks like practically not much intuitive. And you can see the band structure, right? The lattice site space translates into momentum, and cycle translates into energy, and you can see this momentum picture. And you can continue this scheme, and you can see that you have these bound states are forming a band of energies, and this band is getting more and more flat, showing you that the effective mass of the band getting heavier. And according to it's not exactly like your tight binding model, slightly more into it. In tight binding, you have cosine of E of k is cosine of k. Here you have cosine of E of k is cosine of k. So there's another extra cosine, and there's some offsets and whatnot. But on the zeroth order, they look the same. So anyways, Igor in his paper has a very clear analytical form, which this alpha sets by the strength of the hopping and the phase accumulation term, and you can construct this very nicely, and you can see that it does. So again, trying to please the condensed matter people in the audience, I can say that these fsim gates, which is the unitary operation that we do, can very easily pick up a synthetic gauge field. And this gauge field is gauge invariant, this beta parameter. The sum of it is gauge invariant, because we are forming a closed loop and cannot be factored out. And we can change this beta factor on individual qubits, on the individual gates, in 2-qubit gates, and then as a result of it, on the horizontal axis. I'm showing you how this flux is changing it. So this is saying that in this setup that we have on every closed loop, we can really easily put a synthetic gauge field, and the pseudo charge of the band, of the particles making this band in the condensed matter analogy, would be extracted by saying how the band shift as you start putting momentum in it. I'm showing you for 2-photon case, you see a band, and you see this band is sliding in front of your eyes as a result of putting flux into this loop. And I can use that to extract, this is this case, I extract essentially a charge, effective charge, right? Response to the flux tells you about the charge. And again, from the paper by Aligner, there's a very simple prediction, and you can see that it's really matches in there. Just so you see the limitation of the device, these results may look very, I don't know. I want to emphasize that these are not very easily obtained. This is kind of the limitation of the processor at the moment, and this is what we can do unless we get far better in coherence or data taking rate and make lots of technical advancement. The data that you see in here is not coming from, first of all, I want to emphasize that is not coming from someone eyeballing and putting dots wherever they felt is a good place for them. Is really coming from convoluting the bands by themselves at a later instance of time, and extracting the peak, so it's really done properly. But also I want to tell you that the 5 photon case, which I told you it takes about 32 Pauli operators to be taken and added up properly together, it took about 100 hours. So it's not easy, in case you were wondering why we didn't do 6 or 8 photons. First, there's a coherence battle. Second, there's a time battle in terms of what it takes to do this experiment. So I'm happy to highlight the shortcomings of the method. So let me go a little to the discovery phase and talking about going beyond the known physics, about the Achilles heels and the integrability. Clearly, we got a message from our advisor and spiritual leader telling us that, well, we got to break integrability. Otherwise, we are just confirming what is known by theory work. So the way to break integrability, or rather one way of breaking integrability, is to add go to extra dimension, or to the, I don't know, go out of the loop toward the second dimension, meaning that we add an extra qubit to every other qubit. So in a chain of 14 qubits, we are adding 7 extra qubits. And these 7 extra qubits take you from 14 to 21. The Hilbert space become 4 times bigger, effectively. So in the gate sequence I showed you, after the gates that we discussed, now I'm going to add another gate, which is try to get the excitation out of the gray ring and get it to the red new qubits. Okay. So let's see what we expect. We are breaking the integrability, which was the underlying physics that exploited to give us these bound states. As now we have the band structure, if I go and put this band structure on top of each other on the proper energy range, you would see that, for instance, a 3-photon case is overlapping with single excitation ones. So as soon as you break it, you would expect that this decays into this, with probably you would use Fermi golden rule, and don't take this super literally. I mean Fermi golden rule, and you have to figure out what is rho and what is, I don't know, is this bound state overlap with, anyways, there is an overlap component and there is a density of states at the Fermi energy, or in this case, at the place of the energy of the band. I don't mean specific, is the job by itself to figure out what goes in here. What I'm trying to say is that it tells you how you intuitively think about this problem. And probably you are getting the feeling that I'm setting the stage to say that this is going to fail, and this is not the case. So let's go focus on the strength of this bond and make it, starting from where we can make it stronger and stronger. So on the vertical axis, I'm showing you the ratio of the bit strings that are together to the total ratio of the bit strings that I collected. If the bound state is intact, this line should be flat as a function of cycle. In the real experiment, it is not, and is decaying with certain rate out to decoherence and whatnot. But what I'm telling now, the other curves are when we start to make this perturbation stronger and stronger. So again, the Fermi golden rule, or thinking along those lines, suggests that as soon as this perturbation becomes as strong as the dynamic generator of the dynamic in the main loop, you would just drop dead and you go very, very low, and you break the bound state. However, this line, which is what you see when the perturbation is super strong, theta prime is about pi/2. But at the theta prime, close to theta pi/6, you would not see that much decay. Let me show you further more data that shows that indeed the bound states stay intact for the values of the perturbation, substantial value of the perturbation. Let me make 2 cuts into this plot at 2 different cycles, which you can see, this is the same data shown differently. And you can see that for very early cycles up to pi/6, in fact, which is in fact the strength of the coupling in the main chain, the perturbation does not do much, which is very counterintuitive. You would think that as soon as you turn the perturbation, the bound state would be gone. But it's really slowly decaying up to a very later instance of time. Okay. I can go and look at the momentum picture and ask the same question. So we look at the bound, the width of the band structure, the band that we look together, and now to make the perturbation very strong, it goes away. But the question is, how does it go away? And you see it with very strong perturbation, the full width half max of this peak is very much remains intact and then eventually goes up. It's very sharp contrast to the intuitive picture that could come from naive implementation of the Fermi-Golden rule. So we have a puzzle. It's not, I would say we have a discovery, and the significance of the discovery can be discussed, but of course it's not a major discovery, but it's something that I very much like to say is in the line of starting from theory and going to experiment. Starting from experiment and inspiring theories to think about why this is happening rather than experimental work only confirming the existing theories. So going with this puzzling result around, I would say that very clear or intuitive picture of what is happening here is still missing. Are there any conserved quantity? Was there idea of breaking the integrability in this way I showed you? Was it really viable? The answer is no. I show you the data for it in a second. Prethermalization is a very general framework that we might say, okay, maybe it can explain it, but I want to highlight that the known works in the prethermalization always focuses on very small perturbation value and not such a strong perturbation. And prethermalization is rather a vague phrase such that you cannot really refute it. It's anything can be classified in that in a sense and can be attributed after fact too. So it's a bit strange. Are there any emerging symmetries that protects these states? That I don't know. This was proposed by John Preskill. I don't know what to say there. But anyways, these are I'm very happy to receive stimulating suggestions and getting people to think more about this problem coming based on the result that is coming from the hardware processor. And then only after fact, Dima Abanin confirmed that numerics also show the robustness of these bound states in a sense that he could go with some well, either small sizes or doing certain truncation of the bond dimension. You could go to very large sizes and deeper circuits, but at the cost of creating errors by keeping the entanglement growth constant. You could see that some certain simulation can be done, which confirms that this, in fact, the states are very much robust beyond what we could imagine. And also I could show you the level spacing that shows that the idea we use to break the integrability in fact makes sense. The level repulsion is in place as you go to these parameters, meaning that the entire Hilbert space is effectively participating in this business. So it's not and their levels are repelling each other. If the levels couldn't care about each other and wouldn't sense each other, would follow a Poisson distribution. But we see this circular orthogonal ensemble indicative of the fact that, in fact, these extra dimensional of the Hilbert space are indeed available and are sensed by each other. Their levels are pushing against each other. Okay, so I'm going to go to another idea, another project, which is now maybe getting closer to borderline of condensed matter and error correction. But maybe there's a question, or maybe I keep going. All right. So this is a different project, and this is done in collaboration with several academic groups, and is getting to the question of realizing phases of condensed matter on our platform. So we have one way of seeing phases in condensed matter systems, or of course coming up with crystals that are promised to have these properties, and we are familiar with the challenges of those physics in terms of controlling stoichiometry and defects and measurement, limited measurement offers we have. And we have our own challenges. And I chose this realization of the Kitaev model, which is a solvable model that is written to have topological orders. So imagine a Hamiltonian on a lattice that terms are either, well, that the qubits or the spin half particles are interacting with each other, either with this plaquette term XXXX on each plaquette, and also or as well they are interacting through with these ZZZZ terms. So this is a model which is written to because Kitaev knew it is going to have topological ground state essentially. But for us, the challenge is to create such a topological state which is long-range entanglement, and coherence of our system comes to bother us when we are thinking to realize it. Nevertheless, we could, I'm showing you the expectation value of these individual terms. So meaning that we made the wave function, I'm about to explain how. We made the wave function, and after we made the wave function, we performed this expectation value measurement, and every time I did the Z parity measurement, I put it in here with these blue ones, and the purple ones are showing you the X parity measurements. So we did not realize the phase, but we are making a non-equilibrium state, which is not the ground state of the system. So it's a very distinct approach, but nevertheless, it could be interesting to see some physics, and this is the essence of what error correction physics likes us to do. So I'll get closer to that in a second. The cleverness of Michael Knapp and Frank Polman and in their team was to come up with a scheme to make this circuit in a very shallow number of steps. Basically, with you let the qubits sit there, they will get to 0, 0, 0, 0, and this would be your expectation of these operators. But you can apply Hadamard to a top of each plaquette, and by getting clever on the order of the way you apply C naught gates, you can propagate this, you can entangle the qubits and propagate this entanglement, and you can arrive at this configuration that you are seeing in here. Essentially, the whole scheme is rest on the insight that the ground state of the system is the superposition of all possible plaque configurations. So when you know that, then you can start to write very effective pulse sequences. So the effectiveness in here is that the number of steps in this pulse sequence goes linear, or is the number of one dimension of the system. It's not scaled with the X and Y, but it only scales with one dimension. You can see that there is a row, or there is a column of operations, and you're propagating outward. So here I'm showing a little, or here I'm showing you exact scaling, where n is one dimension of this width of the plaque, number of plaquettes, I guess. And here see the detailed steps that it takes to do it, and the bigger and bigger super positions that are made after each steps. But also I want to make a full disclaimer that in this case, just to look good, we can do some readout correction. Every readout is done locally over 4 qubits. So you could apply a readout correction, and you can see before and after. And we borrowed the idea that implemented in this paper very, very nicely. And you can see that to some extent things can be corrected. The hallmark of these topological states is their topological entanglement entity. Yes. Okay. And the first thing I want to show you is to show this topological entanglement entropy. But the idea is that when you look at the patches of qubits, they have an entanglement entropy that is coming from their entanglement with surrounding qubits, but there is another contribution to it, which is this is one universal number, which is the topological entanglement entropy. So basically, if you could measure entanglement entropy of subsystems, for instance, you measure consider this case. When you measure SA, you get contribution from this edge and this edge and this edge. And then SP, and so you keep getting contribution from these edges and these lines that you're essentially crossing. But if you really come up with a proper addition and subtraction, you can remove all these contribution that comes from these edge effects, essentially, the local effects, and you would be left with some universal number. In the absence of topological entanglement entropy, that number would be 0. For these ground states, it has been predicted to be -1. And the recipe that comes from the for this Hamiltonian is super simple. If you want to know the entanglement entropy of this subset of qubits, you draw a circle around it, you draw a loop around it, and you see how many plaquettes is cutting. You count the number of plaquettes, -1, and you put a log of 2 there because you want to be sure condensed matter people and computer science people are not getting into fight. And I don't know, one of them want this, one of them don't want this, so you just put it in there. It's a strange thing to do, but you would do it anyways. So I'm saying that checking the results is rather trivial in this case, in fact. But the point is, did we realize it in our chip? So let's focus on this 2x2 case. You can go to subsystem of 1 qubit, that's the size of the subsystem, and you can measure their entanglement entropy, and lo and behold, you get 1. You can go to all possible configuration of 2 qubit subsystem, and the numbers you get is 2. The entanglement entropy is 2, and so forth. Then when up to 3. When you get to 4 qubits, you can imagine 2 configuration. One that has doesn't have internal inside, another which is more open and you can see inside. So this one is cutting 5 and this one is cutting 4. So this is the first real test that you have done it, that this thing works, meaning that you measure entanglement entropy of 4 qubits. If it's this configuration, you have to get 3, and if it's this configuration, you have to get 4. And when you go higher size qubit configuration, you would have, you can get more distinct numbers. But then let me highlight the experimental challenge of how we measure entanglement entropy. Up to some point, of course, you can do full tomography. You measure all Pauli operators, you put them in a density matrix with max likelihood, and trace the rho squared gives you the second order Rene entropy. But then as the system size get bigger and bigger, this procedure would not be possible. You need to look at this term, SABC, meaning the entanglement entropy of this large system. Let me see. Well, we use this approximate relation, which was proposed by Peter Zoller and his team. Sorry, I forgot to cite them. Which tells you that basically do a random measurement. If you do random measurement at the end of the sequence, is sufficient to tell you the approximated trace of rho squared and give you an approximation for second order Rene entropy. And so while the whole experiment takes about a few hours, this last piece of measuring entanglement entropy of a subsystem of 9 qubits could take you a night or a day or so after you know what you're doing. So you have all these pieces together and you can go and add them up correctly. And then you can see a histogram of topological entanglement entropy over all configurations that we could go and look for this number. And you can see it's close to -1. There is a distribution, it's close to -1. And we would, okay, I put the log 2 in here. We take this as indication that indeed there is a topological entanglement entropy on this system. Okay, creating an excitation and braiding them is really essence of doing logical operating with them. So let me get there first. And here, basically, the idea is that if you apply X rotations or Z rotations operations to qubits, you create an E pair or M pair. And if you start from the, well, usually you create a pair if you do it in the middle of the chip, but you can get clever and apply a Z operation in the corner of the qubits, in a corner qubit, and you can create one of the quasi-particle excitations. And you can create E and M, and you can manage to move one of them around each other, and you come back with a global phase. So now the problem is that this global phase is predicted, but if you look at them, they don't look different from each other from local measurement, and the global phase is not measurable. So you need to be slightly more clever, or you have to partner and find collaborators who are more clever than you, and that would also work. So what I'm saying is that there is a wave function which you evolve under this operation, gets a global phase which is not measurable. However, if you conditionally couple the operator to an ancillary qubit, an external qubit, then this phase very nicely would go to that ancillary qubit and can be measured. And that is what we are going to do for all these configurations. So there is an extra qubit, ancillary qubit is standing out there. And you can see before and after, when you do local measurements, you don't see a difference. But the measurement on the ancillary qubit would tell you the phase accumulated over the process. And now we can literally, or not literally, we can go to town and measure create all possible quasi-particles or abelian defects and braid them together, and we can see the exchange statistics and the mutual statistic by creating E and E particle going around each other. E is the name given when you apply a X to a qubit, and M is the name, has to do with E and M, their origination. It's a historical reasons. And you can see that the phase accumulation is either is 0 or pi, and you can see the semionic statistics and whatnot. Okay, let me try to bridge to a surface code physics and making a qubit gates with them. So basically, we can start with what we're asking is that can we make a logical qubit, a 3x3 logical qubit, or 5x5 logical qubit made by 5x5 group of qubits, and do we see any improvement by going bigger? Long story short is that this experiment was done a few years ago at the limit that we didn't see much improvement without error correction. There is no active error correction in place, and we are not seeing much improvement. And we did a very simple post-processing correction. Basically, I'm introducing the X gate and Z gate for you, and then, logical X and logical Z. And you can imagine the procedure that I showed you to ground state. You can modify it in a slight manner, so you can make the superposition of 0 and 1 and everything in between by just modifying this procedure slightly. It's nothing fundamentally different. It's just a slight modification of that procedure. And you can make all different points on this logical block sphere. And you can see that the points are unfortunately not on the surface of the block sphere. They are a little inside. But also, as you do a measurement, because you're doing a logical measurement, you can see that there is inconsistencies, and you can use a very simple algorithm to do post-processing correction on this logical measurement. And you can, and this works to some extent. So let me show you some results. Let's say on the 3x3 case, you're measuring plus states, and you get a, well, yeah, when you start to inferring what the value of, and you put the logical qubit on the block sphere, on the equator of the block sphere, and you say, did I stay there? And the answer is, well, you're getting more and more error as you keep doing the procedure. The simple correction that I suggested can bring you down, and then furthermore, you can start a decoupling idea, which is just we should have done it to begin with, which is some dynamical decoupling, not letting qubits idle for a long time during the circuit. If you see a void regions in the circuit, you should put a X gates and whatnot so qubits don't dephase. That simple idea brings you to this baseline. You can put a qubit on the North Pole or South Pole, and you can repeat the experiment. Again, the correction idea I'm suggesting in here can help you to some extent, but at some point it's just failing. It's just not going to help you. And the error, your identification would be just getting more and more erroneous. So you can come to the 5-qubit case, and you repeat the experiment again, the error rate's going higher, but when you start correcting again, you would come down. But you don't see magic there, you know. It's very hard to argue that these last points are better than these points. I would not go that far. I would say that we are not clearly over the threshold or under the threshold that making larger systems are making better qubits, at least at the time of this experiment. So that suggests that, okay, there's only certain physics can be done in here without active error correction, and that would be the subject of the future discussions. So going back to this plot, I'm hoping that I gave you a little flavor of how NIST discoveries are going to look like. And my prediction is that they are going to belong to the category of non-equilibrium dynamics. And I showed you our capability of making synthetic gauge field, making band structure measurements, and essentially doing this and realizing these quantum phases of matter and answer very limited sets of questions. So don't expect miracle from us, and error correction is a whole different package that we can discuss later. I can, I want to stop now and take questions. Thanks for listening to me.
Thank you, Pedram. So I guess people, if you have questions, they can just basically unmute yourself and ask questions. Any questions from the audience? Okay, maybe I can ask a question while I guess people are warm up to ask questions. Can you say a bit more about well, I mean, actually, I have questions about both the error correction part and also the sort of measurement process for measuring the phases when you braid the abelian particles. I mean, whichever order you want. I mean, if you can just basically maybe say a bit more about how the process of like measuring the like how exactly you measure the phases again, and also where do you see we're going with the error correction, like how like what are the main challenges, and when we're going to get to the point that we can actually, you know, not necessarily with thousands of qubits, but just basically do proper error correction with just a small number of qubits.
So, okay, well, maybe, do you see the slides? I don't know what this, okay. This case is it should not be mysterious, right? You prepare the ground state of the toric code according to the procedure I said, and then you do the braiding according to these steps. But then the key is that you're doing this gate essentially. You're entangling your U operator to an external qubit, to another additional qubit, which is just accumulating the phase, is watching you to accumulate the phase. Okay, and the measurement is done on that qubit. So everything comes from the phase measurement on that extra qubits. So you repeat the procedure, you measure everything, you measure it, you get a value of 0 or 1, and then you measure the experiment, repeat the experiment 10,000 times, and you average them, and this is what we do mainly every day. Okay. Here, there is no active correction. There is no active error correction. And basically, this is the Z logical Z measurement. You measure on the Z basis, you measure the Z state of these 4 qubits. And then if you see something funny, which some of your plaquettes light up, which you shouldn't light up, then you would use a very simple argument later in your classical processor. Say, oh, if I flip these 2 things, red things go off. Oh, let me do that. You just do it with a simple algorithm which has that logic. What's the minimum number of changes I have to make to restore my value? So what I'm saying is, when you're doing Z logical measurement, you're not only measuring this row, you're measuring the whole plaquette measurement, and you use that information to correct that. So this is a typical outcome of the measurement. You put them together for the plaquette measurement, you color the plaquette measurement, say, oh, there 2 things went wrong. Oh, look, a simple, this is the minimum fix that fix my red things. Okay, let me do these things. Let me flip these 2 values by hand afterward and say, okay, this is one of my measurements. And then you repeat the experiment over and over again with this logical way of thinking. And what I'm telling you, that in spite of all that, these simple algorithms sometimes just doesn't work, and you have to go faster, more fancier decoding and whatnot, which it doesn't, is not the point of this article. The point is to show what can be done, is not to really get the most out of the system, or actually, to me, is highlight the shortcomings. But maybe I'm answer the measurement question.
Right. Yeah.
Okay. So, but also I would say is a very exciting time in terms of error correction. That and these, I see is a time that we don't need to really stick with the. There could be other clever ideas. There could be other logical states that provide some benefits without going to the standard established. You see, we are at the point that various ideas can be checked. I'm sorry I'm not talking about the non-Abelian work, but the point is that some of those are inspiring to think that, okay, maybe there are other logical states can be made that are inspired by the hardware rather than the established mathematical frameworks over these many years. Now you can sit back and say, I cannot articulate very well in here. You can sit back and see what is feasible on the hardware and think about other logical qubits that can be made. But as far as in our end, unless you make much better qubits, you cannot get much better. You're always, current technology, I would say, at least in our lab, is you really land on the fuzzy region of the, every time we ask, is going bigger is better, we are not clearly over the threshold. The answer comes at which day you ask the question or which data set to look at. We want to be order of magnitude above the threshold, and we are just barely above the threshold, and we are struggling a lot, and then we're making more clever decoder and whatnot. But the focus should go into make the qubits genuinely much better.
Okay, makes sense. Thanks. Any other questions from the audience?
I guess I can ask one, but I'm not sure if it makes much sense. When you were talking about how you do this like band structure reconstruction, can you go back to those slides? Yeah, maybe a few more before. Basically, when you said, yeah, this one. So if I understand properly, basically you want to extract the values of the phase that you get, right? As you evolve, and basically this gives you the different energy levels. Would it be possible to also, as you evolve the system, like try to do some adiabatical transform to also try to extract like the geometrical phase of a system, like to try to determine the topological properties of the band structure at the same time at which you unveil the band structure itself?
I can imagine, but that could be a different procedure, no? I see. You're thinking more like traveling along the band to go over the Brillouin zone and integrate or something and get the Chern number of the band.
Right.
Yeah, I don't know. There are some proposals on that, but I don't know if they're related to this. This is more like, well, in some sense, is a pump probe measurement, and I don't know. I have to see a procedure. It would be nice to have a procedure there. Yes, there are some work on that, but I'm not familiar. Yeah, here is just, I think the single particle I saw on the left meant to say that it's very rudimentary physics. I don't know. Well, because we didn't create a package with a given velocity, so I don't know.
All right. Okay. Thank you.
Sure.
Any other questions? Okay, maybe I can ask one more question. So what is next? What are you, I guess, what's sort of the next big experiment you're planning, if you can share?
Oh yeah, definitely. Let's do that on recording. How about that? I'm very passionate, and I invite everybody to give us suggestions on what are the, as mentioned several times, the beyond classical experiment of 2019 was a contrived, well-posed and contrived problem. It was well-posed, so it's good. We can really put benchmark on it. But was contrived at the end of the day. It was very much cart in front of the horse. We know what to do, which gate to use, and go to ergodicity and whatnot. I'm wondering what are the problems in non-equilibrium physics that can be mapped, that is maybe less contrived, that there is some people are wondering about them, and we can use our platform to address them. I'm really much interested in that, and I know what the answers are not. I know the answers has to be a 2D problem, and I know the answer probably cannot be a ground state problem. It has to be some non-equilibrium, away from equilibrium, away from ground state. We are not very good in ground state. The problem could be possibly cannot be coming from electron physics, correlated electrons related to high TC or anything, because those need Jordan-Wigner mapping, and we are not good at that. So I eliminated lots of problems. So the problem cannot be optimization, because we are not good at optimization. It's not meant for our hardware. And the example I amplify in the first part of the talk, I don't know if it impressed people or not, but it meant to say that this is how things look like realistically. You put 5 photons in a 24 qubits, that's a Hilbert space of 8,000 dimension. And you can say something that, theorists didn't think about it before, but as soon as they know about it, of course, they can do everything with it now. So I'm trying to expand on that frontier, and I'm very open to suggestions and ideas, yeah.
Sounds good. So last chance from the audience to ask questions.
Maybe I can go with
Go ahead,
one.
please.
Yeah, so you're saying that it's not possible to get like ground state properties, right? I mean,
let me interrupt for a second. We can is not where our strength is.
Okay. So what I
That's
was,
what.
I was thinking about, like, maybe since you're describing these topological phases, so is it possible like to simulate something like a quantum spin liquid Hamiltonian?
Yeah,
or-
actually that's a good point. So let's talk about that.
Yeah.
If you say, well, so it comes down to this: can we make a spin liquid looking state?
Mhm.
Do we have a Hamiltonian that is ground state as a spin liquid in our platform? We have a square lattice.
Yeah.
We cannot have 6 connection of the triangular lattice. We
Mhm.
can kill a connection and make a honeycomb lattice.
Yeah.
That could be inspiring.
Mhm.
We can go to 4 connection per qubit, 3 and 4, but not 6. So this is a big clear. But you can think about, okay, in either of these two geometries, you can entangle, make these valence bound states between neighboring qubits or diagonal qubits. You can do that kind of thing. And then you can get clever to make a bigger superposition, right? Making a bunch of dimers is not hard. And then you can say, well, can I do some flipping that I can make a big superposition? That is probably not hard either. And now is where you enter what to do with it. I don't have the Hamiltonian, but you might say, well, if you go with second order couplings, next nearest neighbor, you might have the genuine Hamiltonian. I would be very happy to see that. And then again, you come in to tell me what to measure.
So so what I have in mind is, so you said, like, okay, so if there is a spin Hamiltonian, let's say local interaction, so is that possible? Because there are some proposals.
Yeah. Well, no, yes and no. I mean, maybe that's a good point. Let's go back in here. Well, if you think about this is a Hamiltonian if you want to think about it, but we do the Flockhead version, meaning that is not the genuine trotterization, is a trotterization of this Hamiltonian with the big steps.
Mhm.
So e to the xx plus yy and e to the zz are not small, so they don't commute, right?
Yeah.
And this is essentially this unitary. But look at in here that you see that there's only nearest neighbor coupling.
Mhm.
You can say, Pedram, that's not good. Why can't you go from 3 to 5? We can decompose that. We can think together. There's no gate to do that. We try that. But we can decompose that. But then if you tell me that that's a good, well, if I go and say I have this unitary and I have 2D grid, and I'm going to do spin liquid, I think probably people would laugh at me. So at least we have to go maybe with the next nearest hopping or some, I don't know, exotic case or something we can think about.
Yeah.
But I'm telling is that we should be clever in asking the question. If you ask what's the ground state, I don't have, well, how do you going to get to ground state of a Hamiltonian or a thing? Well, if you do adiabatic, we're going to round out of coherence, and probably the gap is going to be small. But if you say that I make this a spin liquid state, right, that we discussed, it's not that hard, and I create a defect like a spin ice defect recently was discussed. What is the dynamic? What is the diffusion of them? If I make 2 defects and I get them collide, those questions I think we would be able to explore. I just don't have a good procedure. Yeah.
So probably something which can, so there are these recent papers by Claudio Chamon and about constructing this spin liquids using something they're calling combinatorial gauge symmetry. So the Hamiltonians are basically local, depending on, again, local spin interactions, but with a gauge field. So something like that probably could help in some way. I don't know if you have looked into that already.
No, that was very lovely thing, and that's why in fact I try to win your guys' heart by showing this plot, saying that okay, this was the most boring application of it, which is just you put a flux and the band just shifts and moves, but it's trivial to do. This beta, putting this beta there is just super trivial. It's nothing. In fact, sometimes it's not even physical.
Yeah.
You just put it in there.
Yeah, then probably, I mean, yeah, that those kind of ideas are something which probably are gonna help in some sense, I would say. Yeah.
Yeah. No, this is exactly
Mhm.
the purpose of this talk was not to take everything literally, but or face value. Look at it as individual pieces that can be connected
Yeah.
together to solve an interesting physics problem.
Thank you.
Yeah, thank you. That was very useful. I looked into his papers.
Thank you.
Sure.
Great. So one last call for questions. Otherwise, any more? If not, I guess on behalf of everyone else here, so we can clap out. Thank you, Petram, for a great talk.
Yeah, thanks for having
Thank you.
me.